In Chapter 7, we're going to look more at trigonometric identities. In the first section here, we're going to focus on the Pythagorean and the sum and difference identities. Our objectives are to state the Pythagorean identities, to simplify and manipulate expressions that contain trigonometric expressions, and then to use the sum and difference identities to find function values. Quick review. When we say identity in mathematics, we mean statements of equality or statements that are always true. In trigonometry, we have already developed some identities. So here we have a list of our basic identities. These identities, these 6 right here, are the reciprocal identities. We've seen these before, and they go in both directions. In terms of sine of x is the reciprocal of cosecant of x, and therefore cosecant of x is the reciprocal of sine of x. Cosine of x is the reciprocal of secant, and therefore secant is the reciprocal of cosine, and so on with tangent and cotangent. So we already know these basic identities right here as the reciprocal identities. And a few of the other ones in this table we also already know, and we have names for them as well. These identities about sine of negative x being equal to negative sine of x, cosine of negative x being equal to cosine of x, and tangent of negative x being equal to negative tangent of x we saw before. And these were in terms of even or odd function properties. Sine of x and tangent of x being odd functions, cosine being an even function. And the bottom 2 functions we saw as basic identities before that definition of tangent in terms of sine and cosine. Tangent is the ratio of sine of x divided by cosine of x. And then cotangent, of course, its reciprocal is cosine of x divided by sine of x. And so these are just a property or definition of tangent. So we're just going to call that one just a basic identity. It doesn't really have its own name. Reciprocal identities, something about even and odd functions, and the basic identity for tangent and cotangent. So these are identities that we already know and have seen in Chapter 6. The point of this chapter is to expand our list of identities and explore new ways to use them. Topic 1, we're going to look at those Pythagorean identities. Recall that for a unit circle, we can express the circle's equation as x squared plus y squared equals 1. This circle has center at the origin, so no coordinates, x plus 0, y plus 0 right here for x squared, y squared, and a radius of 1. We also know that the x and y coordinates on the unit circle can be written as x equals cosine of some angle theta, and y equals sine of that same angle theta. So putting these 3 statements together, we can find a new identity. Please note in trigonometry and all subsequent areas of math, we use particular notation when raising a trigonometric function to a power in order to avoid confusion. So, for example, we're going to put those things together to make the new identity. I'm going to write this here at the top of this next page. And since x is equal to cosine of theta, when I square that, I need to have cosine of theta squared plus y squared. Y is equal to sine theta. So I need to have sine of theta squared equals 1. So this is the new identity that we're talking about when we put these 2 together. And then we use a particular notation to denote raising a trigonometric function to a power. So we are going to write this as cosine squared theta plus sine squared theta equals 1. And that's just the shorthand, that square going right here is just the shorthand notation for squaring the entire function, cosine of theta quantity squared. Versus if we write cosine of theta squared, that's not the same. That's cosine of theta times theta, not the entirety of cosine theta squared. So we want the square to be on the cosine function to indicate the implied grouping parentheses here, the entire function cosine of theta is what is squared. Often we refer to this identity that we have just written here. Mine's got the cosine squared first, then plus the sine squared. Doesn't matter if you reorder that to say the sine squared theta first, then plus the cosine squared theta. So same identity, just in a different order here. We refer to this as the Pythagorean identity. And that's because it comes from the equation of the circle, which is from the Pythagorean theorem. The x squared plus y squared equals 1. That's a squared plus b squared equals c squared. The c is the hypotenuse, which is 1. And note that we can use any variable to represent the real number theta. It doesn't have to be theta. It could be sine squared x plus cosine squared x equals 1. Any variable can be in place of that angle there. Now, we can develop other equivalent identities by performing some algebraic manipulation on given identities, so long as we don't break any rules of algebra. So we're going to make an equivalent identity by dividing this equation by sine squared theta and simplifying. All right, so sine squared theta plus cosine squared theta equals 1. That's our first Pythagorean identity. We're going to divide both sides by sine squared theta as directed here. And we're going to simplify. When the sine squared distributes, sine squared divided by sine squared is 1, plus this right here is going to be cosine squared theta divided by sine squared theta. And then here I have 1 over sine squared theta. We'll recall from our basic identity page that cosine theta over sine theta is equal to cotangent of theta. So cosine squared over sine squared should be equal to cotangent squared of theta. So we have 1 plus cotangent squared of theta here. Remember that that square is really outside of the cosine. So I've got cosine over sine twice, so I've got cotangent twice. And then 1 over sine using the reciprocal identities. 1 over sine is equal to cosecant. So 1 over sine squared is equal to cosecant squared. So let's write 1 over sine again. I want to write cosecant squared of theta. There we go. Okay. So we've just made ourselves another Pythagorean identity. It is printed down below in case your handwriting is a little messy like mine was there. So the Pythagorean identities, the first one is the sine squared plus cosine squared theta equals 1. The next one is the one that we've just created here. It is the 1 plus cotangent squared of x equals cosecant squared of x. And the third one we're going to get by taking that same initial so I need to update my directions right here. We already divided by sine squared, so now we need to divide by cosine squared. So we're going to take that same initial, sine squared theta plus cosine squared theta equals 1, and we're going to divide both sides by cosine squared theta. That will give us sine squared theta over cosine squared theta plus cosine squared theta over cosine squared theta, which is 1, and then 1 over cosine squared theta, which is secant squared theta. And then our sine over cosine is tangent, so this gives me tangent squared theta plus 1 equals secant squared theta. So this is our third Pythagorean identity. It is its own identity, but all three of these do come from that original one. Remember that our primary functions are sine and cosine, and that we can derive tangent, cotangent, secant, and cosecant from them. So all three of these, though, are simplified in their own right in terms of one of these six trigonometric functions. So three Pythagorean identities. So the next topic is we're going to simplify some trigonometric expressions. Just like with any other algebraic expression, we can manipulate, factor, and simplify any trigonometric expression following the same rules. Simplify can mean many things. So let's take a look at a few examples of what we mean by simplify. Our goal here is to multiply and simplify this expression. So the expression here is cosine x times sine x times secant x plus cosecant x. So since the first goal is multiply, we're going to go ahead and distribute cosine x sine x times secant and cosine x sine x times cosecant x. So cosine x sine x distributes to the secant x, and cosine x sine x distributes to the cosecant x. Okay. These are products, so this is cosine x times sine x times secant x plus cosine x times sine x times cosecant x. We can use some of the reciprocal identities to rewrite this again. So cosine x times sine x times secant x we know is 1 over cosine x. And then cosine x times sine x times cosecant x is 1 over sine x. And from there, we're able to reduce through multiplication the cosine x and the 1 over cosine x, as well as the sine x and the 1 over sine x. And so our result simplifies to sine x plus cosine x. The goal in this one was to multiply and simplify. Simplify can mean many things. In this case, this is simplified because I was able to use identities in such a way to give an answer that had fewer trigonometric functions. So this is going to be simplified. One thing to note when we are working through simplifying, when we are applying an identity, it's a good idea to just write down what identities have been applied, whether it's reciprocal or Pythagorean, just to keep track so that you're able to trace through the work that you've done. So for the next example, in example 4, our directions are to factor and simplify the following. So we have 4 times sine squared t plus 8 sine t plus 4. And the first thing I do notice is that there's a GCF with the coefficients. So we're going to factor out that 4. 4 times sine squared t plus 2 sine t plus 1. And then this is going to be factorable more, noting that this is something that is quadratic-like. Sometimes it's helpful to do a substitution. Let's let u equal sine of t. And then I would be able to write this sine squared t as u squared plus 2 times sine t, which is u plus 1. Then it looks like a quadratic. And so I can factor this, and I can see that I need to multiply to 1, add to 2. So I'm going to need to have u plus 1 times u plus 1. 1 plus 1 is 2, 1 times 1 is 1. So that means that my original would factor into 4 times, in place of u in sine t, so 4 times sine t plus 1, and then sine t plus 1. The middle steps here with the u substitution are optional. It's a way of helping us see how something factors by making it instead of quadratic-like, writing it in quadratic form and factoring. But it's also possible just to factor directly if you recognize that pattern and can see that. Again, 1 plus 1 is 2, 1 times 1 is 1, so it still factors here correctly. The final step is because the two binomials are the same, this is a perfect square, I can write this as sine t plus 1 quantity squared, and this is simpler. In the case of the first one, we said, and I will write this down as well, we said it out loud, that this one is simplified. And it was simplified because we were able to reduce the number, the quantity of trig functions, right? We originally had a whole bunch of different trig functions, but when we multiplied and simplified, we have fewer now in the answer. So it was reduce the number of trig functions. That was one possible meaning of simplify. As we said, simplify can mean many things. In this case, this is also simplified. And there really was only one trig function to begin with. It was sine of x, or sine of t. But we had a sine squared as well as a sine, so we're able to get this down to just a single sine function without the sine squared. So we're able to reduce the degree of the trig function. Or reduce the number of occurrences of the trig function. And that you have both the sine squared and the sine in the same function. This is exactly equal to that function here. It's just been rewritten so the sine appears just once. So it's the number of occurrences, just another way of saying this. Reduce the number of occurrences. Okay. And again, this is a loose definition of what simplified looks like. We need to experience a few examples and see how things can be simplified, and then we'll know what to look for in the future. Okay. Our goal here is to simplify this trigonometric function. This one is, or this expression, this one is sine squared x times cosine x over cosine squared x sine x. One of the things that we might notice right away is that we can reduce exponents. So if I have sine squared x, I can reduce it with the sine x in the bottom, getting rid of the square. Sine squared x is sine x times sine x. So I get rid of one of the sine x's and I have one left. Same thing down here. We'll get rid of the cosine squared with this cosine. I'm still going to have a single sine x across the numerator, and I'm still going to have a single cosine x across the denominator. And then I can make that into a single tangent function. And so again, that our goal is to simplify. And what simplify meant in this case was rewriting this by lowering exponents, by reducing, as well as simplifying meant writing the fewest number of trigonometric functions. So we reduced exponents. And we wrote with the fewest trigonometric functions. Reducing the number of trig functions. Even sine of x over cosine of x, there's two functions. When I rewrite this as a tangent, I'm down to one. So just a few things that simplify can mean here. And we used both of those in the previous page, so we're repeating ourselves. Reducing the number of trig functions and also powers is another way of simplifying. All right, the next goal, add and simplify. So I've got negative 1 over cosine squared x. The negative was originally in the front. I put it in the top just to not lose it. Plus Let's go ahead and distribute this exponent here. We've got sine x over cosine x squared. So let's just distribute this exponent here. There are actually two things that I could have done with this first step. I could have taken the sine over cosine and thought tangent. However, noticing that I have a cosine squared down here, I saw this too and thought if I square both of these, I'm going to have a cosine squared in the bottom, and I'm looking towards that common denominator. So let's go ahead and add these up with a common denominator. So I have negative 1 plus sine squared x all over the cosine squared x. So that's the first thing that we did. Our rule had told us to add and simplify. In order to add, I needed to have a common denominator, which I have here. Now, let's go into another identity. I'm going to be able to go a little more. Let me remind you of the Pythagorean identity that said that sine squared theta plus cosine squared theta is equal to 1. I want to use this, and I want to figure out a way of getting rid of the sine squared and maybe having just cosines left. So I'm hoping to be able to simplify this further. So if I know sine squared plus cosine squared equals 1, I know that sine squared theta equals 1 minus cosine squared theta, just subtracting this over to the other side. And I'm going to be able to substitute or plug this in right here. So I've got negative 1 plus, in place of sine squared x, I'm going to have the 1 minus cosine squared x. Okay, so this is an instance here where I'm using a Pythagorean identity to go from one line to the next. So we're just going to note that here, as in that is what has happened. We've substituted an identity for sine squared here over the cosine squared x. Now we'll continue and notice that the negative 1 and the positive 1 are going to add to 0. So I have negative cosine squared x over cosine squared x, and those are going to reduce fully and give me negative 1. So we were able to definitely simplify this. Negative 1 is a lot simpler than the original here by reducing the number of trigonometric functions. And we had to make use of the Pythagorean identity in order to do that. So this is our first instance in these examples here of using one of the Pythagorean entities. We could see how that was very nice when I had a sine squared function, and the addition to the 1 there really helped me pull this together to get this as simple as possible. Pythagorean entities are only going to be used or substituted when you do have sine squared, cosine squared, or tan squared, cosine squared. Any of the trig functions need to be squared in the Pythagorean entities. If they're not squared, then you're going to be looking at one of your basic identities instead. Okay. Example 7, we want to rationalize the denominator. So this right here is the square root of cosine of x over tangent of x. And what I want to think about this one, rationalize the denominator. Rationalize is a word used for square roots. So let's separate this and write this as the square root of cosine x over the square root of tangent of x. The rationalize word typically means multiplying both top and bottom by the square root of the denominator. So let's go ahead and do that because that is what we've been asked to do here. And then we'll talk about this and simplify this a bit further. But if I read just that word rationalize, it's going to lead me to this process. So I have the square root of cosine x tan x over tan x. Now, I'm going to continue on this. Tan x, using a basic identity, I know that tangent of x is equal to sine of x divided by cosine of x. So I'm hoping that there's going to be some additional opportunity to simplify here. So inside the first radical here, we've got cosine of x times tangent, which is sine x over cosine x. And I also have the bottom, which is just tangent of x. I'm going to leave that alone just for a second and come back and look at this in an alternate view here in a minute. I wanted to do this on the top because for sure on the top, those are going to simplify. So excuse me, simplified right now, we have the square root of sine of x over tan x. Another thing that I would like to say about these is sometimes you need to play with them to see if further adjustments will get them to be simpler or not. And what I am unsure of is if my expanded tangent form will help me simplify. So I'm going to play with it. Let's take a look at sine of x over tangent of x, which is sine of x over cosine of x. If I divide by a fraction, I can multiply by its reciprocal. So this would be sine of x times cosine of x over sine of x, or square root of sine of x cosine of x over sine of x. Now, in this case, square root of sine of x over sine of x is not going to simplify without putting that square root back in the denominator. You can think about this canceling the square root of sine of x in the bottom, but that would not be rationalized. So I'm looking at two final rationalized answers as either square root of sine of x over tangent of x, or square root of sine of x cosine of x over sine of x. And I would say that the one that is simpler is going to be the first one because it has fewer trigonometric functions. So we're going to end here. However, I'm going to get to the second one in a second. So this one here is simplified because it has fewest trig functions. However, there are going to be some instances where you're solving equations in future sections where it may be more important to be than simplified to be in just in terms of sines and cosines. There are advantages to being just in terms of sines and cosines as well. So just a note, there are some advantages. For example, solving equations, to being just in sines and cosines, to having only sine and cosine. So it's not, it did not work out that putting tangent in terms of sine and cosine made us simpler. But in the future, if our goal was to solve the equation for x, that might have been the form we would have wanted to continue with. So it doesn't hurt us to look at both of those. But if the goal was to simplify as well as rationalize, this is probably the simpler form since it has fewer trig functions. Okay. Like I was saying before, sometimes we need to get the feel for what it means to simplify because the steps aren't always going to be the same. We need to understand what it means to be simplified. In example 8, my goal is to express the square root of x squared minus 16 over x squared as a trigonometric function of theta without any radicals by letting x equals 4 secant of theta, and assuming that theta is between 0 and pi half, so in quadrant 1. Okay. So we're starting with x squared minus 16, square root of x squared minus 16 over x squared. And what I have been asked to do is to let x equal 4 secant of theta. This process is a trig substitution, and it's something that you will eventually have to do in Calc 1 or 2 to solve some of the integrals that you work with in those chapters. So we're going to practice the simplification part of it, so when you get into Calc 1 and 2, you're ready when you have to do that trig substitution. So substitution is going to turn x into 4 secant theta, so x squared will be 4 times secant theta squared minus 16 over 4 secant theta, again squared. So inside the square root, we've got 4 squared, so that's 16 secant squared theta minus 16 over, again, 16 secant squared theta. The 16s are going to factor out. So square root of 16 times secant squared theta minus 1 over 16 secant squared theta. Now, that secant squared theta, I need to think about my Pythagorean identities. Let's go back and look on our earlier page. So the Pythagorean identity that had secant squared in it said that secant squared theta was equal to 1 plus tan squared theta. So this is going to be equal to, by a Pythagorean identity, the square root of 16 times secant squared theta is equal to 1 plus tangent squared theta, and then minus 1 over the 16 secant squared theta. So we did that replacement for the secant squared theta here with the 1 plus tan squared theta. From there, we can see that the 1's are going to subtract off. So it looks like I have square root of 16 tan squared theta over 16 secant squared theta. The square root of 16 is 4. The square root of tan squared theta is tan of theta. And we're over 16 secant squared theta. This can be reduced because we know that 4/16 reduces to 1/4. So now we have a tangent theta over 4 secant squared theta. Now, I think we can probably do a little more reducing on this one. Right now, I do have 2 trig functions with 1 square, but I know that tangent is equal to sine over cosine, and secant theta is equal to 1 over cosine, so secant squared is equal to 1 over cosine squared theta. All right. So this 4 times the 1 over cosine squared theta, that 4 can multiply up to the top. 4 is 4 over 1, so it's really a 4 over cosine squared theta. We're going to flip and multiply by the reciprocal. So sine theta over cosine theta instead of divided by the fraction 4 over cosine squared, it's going to be multiplied by the fraction cosine squared theta over 4. And then the cosine theta is going to reduce with one of the cosines from the cosine squared theta. So I'm going to end up with sine theta times cosine theta over 4, or 1/4 sine theta times cosine theta. Now, I would say that would now be fully simplified. I'm sorry, I had to use an extra piece of paper to continue. I wrote a little large here, and it may have impacted your ability to fit it on your page here as well. I had to continue past this point right here. At this point right here, I did have two trig functions, but one of them was squared. And by using the basic and reciprocal identities for tangent and secant, I was able to get down to two trig functions still without the square. So I was able to reduce the exponent even if I kept the same number of functions. So this is ultimately a simpler function than the tan theta over secant squared theta. No exponent remains, just a product of two functions. So this is going to be the final simplified version of that expression. All right, I think that's our last page. Oh, actually, hold on. I just got together. One more page. There we go. I was remembering that this function, or this section here, also was supposed to have the sum and difference identities. We haven't hit those yet. This is now our last page on sum and difference identities. All right, so remember that we can consider the arc length and angle as equivalent, provided we're measuring angles and radians on the unit circle. And this means that any two real numbers can be thought of as both distances and corresponding angles. Building off of this idea, we can construct some new identities. So the sum and difference identities say that for any angles, u and v, the sine of u plus or minus the angle v is going to be equal to the sine of u times the cosine of v plus or minus the cosine of u times the sine of v. Now, I want to emphasize that this is a shorthand notation for writing two different identities, not one identity here, sum and difference identities. So the sum identity, sine of u plus v, is equal to sine of u cosine of v plus cosine of u sine of v. So that's the sum identity. And then the difference identity would be sine of u minus v equals sine of u cosine of v minus cosine of u sine of v. Okay, so this is shorthand notation for two identities, one being the sum identity and one being the difference identity. Similarly, we have identities for cosine, cosine of u plus v, and cosine of u minus v. Note the symbol switch over here. For the sum identity for cosine, you're going to do cosine u cosine v minus sine u sine v. And for the difference identity, you'll do cosine u cosine v plus sine u sine v. So this is just, again, shorthand for those two identities. You can write them out separately. Make sure you go across the top row for the sum identity and across the bottom row for the difference identity. Similarly, for tangent, the two tangent identities for sum and difference. For the sum, you're going to have tangent of u plus tangent of v over 1 minus tan u tan v. And for the difference, tan u minus tan v over 1 plus tan u tan v. So we have our sum and our difference identities for all three of them. So this is actually 6 different identities, 3 sum identities and 3 difference identities. 6 identities here for both the sum and the difference. The sum and difference identities can be very useful for finding the exact trig function values of angles, such as the angle 5 pi 12 or 65 or 165 degrees. So think about 5 pi 12 for a second. 5 pi 12 is not on the unit circle, but I wonder if I could make it from angles that are on the unit circle, such as pi 6ths or pi 4ths or pi 3rds or pi halves, etc. So one of the things I noticed about 5 pi 12 is, of course, that the denominator of 5 pi 12 is 12. And if I used two numbers like pi 6 and pi 3rds, their common denominator would be 6. But if I use numbers like 6 and 4 or 4 and 3, their denominator is going to be 12. So I know I'm going to have a 4 in the denominator. So let's see if we can build up to 5 twelfths with a pi 4ths. So I need to take 1/4 of pi plus something and get 5 pi 12ths. So I'm actually going to go backwards here. What is 5 pi 12ths minus pi 4ths? It's a 6th. So we must need to take 1 pi 6th plus 1 pi 4th to get 5 pi 12ths. So just kind of working backwards and thinking about what potential denominator values you would need in order to get a common denominator of 12. I knew it couldn't just be a 6 and a 3 or a 6 and a 2 because the common denominator would be 6. The only way to get a common denominator to be 12 is going to have to be with either 4 and 6 or 4 and 3, right? So it turned out that these are the two that need to be added to get 5 pi 12ths. Okay, that's how I figured out which two angles to use. Now I'm going to write the sine of 5 pi 12ths as the sine of pi 6ths plus pi 4ths. And we are going to use the sum and difference identity, sum specifically identity, to separate this into the sine of u. So u and v are just the first and second, and it doesn't matter which one's which. So this one's going to be u, this one's going to be v. So we need sine of u, which is sine of pi 6ths, times cosine of v, so cosine of pi 4ths. For the sum identity, it's going to continue to have a plus, so plus, and then cosine of u, so that's cosine of pi 6ths, times sine of v, sine of pi 4ths. Okay. Now, these are special angles, so I know from the unit circle the sine and cosine value. The sine of pi 6ths, I remember that pi 6th is the shorter, longer angle, so the sine is going to be the smaller, it's the 1/2. Cosine of pi 4, sine and cosine of pi 4s are both root 2 over 2, so it's going to be root 2 over 2. Cosine of pi 6, that's the longer one, so it's square root of 3 over 2, times sine of pi 4, that's root 2 over 2. You can look this up on the unit circle. And so I'm going to end up with square root of 2 over 4 plus square root of 6 over 4, or square root of 2 plus square root of 6 over 4. Okay. So I can find the exact value of this. Now, I would not have been able to do that on the calculator. In the calculator, if I wanted to find the sine of 5 pi 12ths, it comes out as this decimal. But I can check that this decimal is the same thing as the square root of 2 plus the square root of 6 over 4. So yes, it looks like it's the same thing. I was able to use the sum and difference identity to get the exact value for an angle that was not originally on the unit circle, but can be built from two angles that are on the unit circle. Let's do this again one more time. This one's in degrees, 165. So I'm going to try to build 165 out of special angles. So we're going to build it out of maybe a 30, a 45, a 60, a 90, etc. Now, I know that 165 ends with a 5, so a 45-degree angle is going to have to take part in there. So 165 minus 45 gives me 120. And 120 is one of the special angles. It's in quadrant 2, but it is one of our special angles on the unit circle. So let's just use those two. So if we take 45 degrees plus 120 degrees, it does give us 165 degrees. So cosine of 165 degrees equals cosine of 45 degrees plus 120 degrees. So for cosine, the sum, again, u is going to be 45 here, v is going to be the 120. And for the sum, we are going to take the cosine of u, which is 45 degrees, cosine of v, which is 120 degrees. We are going to subtract sine of 45 degrees, sine of 120 degrees. Okay, cosine of 45 degrees, it's square root of 2 over 2. Sine and cosine are the same at 45 degrees, which is a pi-4 angle. 120 degrees is 30 degrees past 90. That's where 120 would be, right? And this is where 90 is. So it's got a reference angle that's the same as that 60-degree angle, since it's equally taller than it is wide. So its cosine value is going to be a half, but it's going to be negative a half because it's in quadrant 2. Minus the sine of 45, which is another root 2 over 2, and the sine of 120, which is going to be positive. Sine values are positive in quadrant 2, and that's going to be our positive square root of 3 over 2. So here I've got a negative square root of 2 over 4 minus a square root of 6 over 4. So we end up with negative square root of 2 minus square root of 6 over 4. Or negative square root of 2 plus square root of 6 over 4, just another way of writing it. So it's the same number as we had over here, actually. It's just going to be negative. So let's check. I still don't have that number. See if I can undo and get that number back. There it is. All right, I do need to switch into degree mode. And now I can do the cosine of 165. It's negative of the square root of 2 plus square root of 6 over 4. The value matches up. So we've got our value here evaluated correctly through that sum and difference identity. All right, now that is our last page for the section.